Hi everyone, this is John and Jacinta from Monash University, and today we want to introduce a simulation on buoyancy, which help you to learn more about buoyancy and Archimedes' principle. So the simulation that we're using is from FAT website, so that it is developed by University of Colorado for educational purposes, so it's free of charge. So if you go to FET website as shown here and then go to simulation, so if I click on simulation, that will bring us to all the subjects that's available. So we've got physics, so go to physics, then go to motion. Down the bottom you can see the buoyancy, the topic on buoyancy, so click on that, so that will bring up the simulation, so you can click on that button to run the simulation. So here it is. So here is the simulation that we will talk about today. So you've got the flute there, so that currently it's water, but you can change it to oil, and it can change back to water, which has a known density of 1000 kilogram per cubic meter. I hope that everyone know about that. So you've got two cubes here. One is made of wood and the other one is made of brick. So you can drag any of them and throw that into the tank. Okay, you can use that one as well. Bring it up, and you can see that the currently is 100 liter mark there. So the volume of water is 100 liter, and when you submerge or put some block or one or two, but just first one in, you can see the volume change. So that is 5 liters. So it changed from 100 liters to 105 liters. So that is 5 liters. It means that the displaced volume of water is 5 liter, and from that one you can work out by hand the buoyancy force acting on the object. So this object is floating, so it is actually in equilibrium. So the forces acting on it have to balance out. So you've got gravity force acting to it, and also the buoyancy force acting to it as well. You can show the force values. So 49 newtons acting up as a buoyancy force, and 49 newton acting down, which is gravity, which can be calculated by mass multiplied by the acceleration, the gravitational acceleration g of 9.8. So 5 times 9.8 will give you that 49 newton. And also you can work out by hand to justify the 49 newton there. So you've got 5 liters of water is displaced, and now I bring up the Archimedes principle as well, so we can refresh our mind. So Archimedes principle indicates that the upward buoyant force that is exerted on a body immersed in a fluid, whether fully or partially submerged, is equal to the weight of the fluid that the body displaces. So that force, the buoyant force, is equal to the weight of the fluid that the body displaced. So in this particular case, the displaced volume of water is 5 liter. So if you time that by the density of water, times it by the gravitational acceleration, then you will have 49 newton as well. So this object is in equilibrium, so the net force is 0. Okay, so through that you can see clearly how the buoyant how the buoyant force is acting, and see how Archimedes principle is acting in place in real life. Okay, so the next I want to remove the force values and also the force arrows, so you can move that away. And now you put the second block in, which is the brick. And in this case, you can see that the object sinks right down to the bottom. Now I wanted to do two things. First, I want to weight this block in the air. So it's 49 Newton as well. So it's 5 kilograms multiplied by G for 49 Newton in the air. But in water, you weight it in the water, it is actually 24.5 Newton only. So what happened there? So you can show gravity and value as well. So you've still got 49, but then you've got a buoyant force. You've got a buoyancy there. The buoyant force is 24.5 Newton, and therefore the scale will show 24.5 Newton, which is the reaction from the scale onto that particular object, and it is in equilibrium as well. So you've got force acting up, which is buoyant force. The reaction is 24.5 Newton as well, and the gravity of 49 Newton. So again, this buoyancy or the buoyant force can be calculated by working out the weight of the displaced volume of water. So in this particular case, if you look at this figure here, which show 102.5 liter from the initial volume of 100 liter, so you can see that the volume change is 2.5 liter, and in fact that is the displaced volume of water. So you multiply the 2.5 liter by the density of water, and then the gravitational acceleration factor G of 9.8, that will give you that 24.5 Newton for the buoyant force. Okay. Now, the next question is as to why the two block, both 5 kilogram, one is floating and one is sinking. So that is all about the relative density of any object or any material or any block in comparison to the water. So in the first case, when the material density is less than the water, so you see the weight of the whole block is equal to the weight of the displaced water, which is just partially not the same volume as the whole block. So the smaller volume of water weights the same as the whole volume of the block. So it says that the block density is actually less than the water, and in fact you can actually work out the density of the block. So if I remove the masses, the force values and everything else, and I drag that things inside the water, you see the volume change from 100 to 112.5. So the volume of this block is 12.5 liter, and you know the mass, which is 5 kilogram. From that you can work out the density of the block, which worked out to be about 400 kilogram per cubic meter compared to 1000 kilogram per cubic meter of the water. Okay, so that is for the timber. And for the brick, 5 kilogram, but the volume of this block is 2.5 liters. So it changed from 100 liter to 102.5 liters. So the volume of this block is 2.5 liter. So therefore the density is 5 kilogram divided by 2.5 liter, which worked out to be 2000 kilogram per cubic meter. That is double the density of water. So that explains why the object sinks. Okay, so other things that you can do with this program. So if you've got more time, play around with it. But in the buoyancy playground, there's a lot of other things that you can do. So currently, it's a wood. So we talked about it before. So 400 kilogram per cubic meter density. Oh, this is kilogram per liter, which is a bit abnormal. But anyway, that is 400 kilogram per cubic meter, and then you can change the block. You can change. Hang on to see whether I can change it. Okay, if you can change it to aluminium, and then it's much heavier, and the density is 2,700 kilogram per cubic meter. That's much heavier than the water. All right, so a lot of things that you can play around with this simulation, but we hope that you learn something more or reinforce or really strengthen your understanding about buoyancy and Archimedes' principle. Thank you very much.